Section 2.3, we're talking about transformations of functions, namely parent functions, okay? The cool thing about this is if you know what a starting graph looks like, whether it's x squared like we had in the warm-up or some other function like square root of x or x cubed, you might have seen those memes. It's like the math dance, and it's a little stick figure guy, but his arms are all waving in different directions, and it tells you what the mathematical equation is underneath there. If you know what your starting graph looks like and you know its equation, you can actually make changes in the equation and know exactly then how that's going to affect the graph. If you make a little change in the equation here, you know it's going to make a change in the graph exactly like this, and then you can actually sketch that graph without using your calculator, okay, because you're thinking and it gives you more information about the function. This right here is called standard transformation form. It assumes that we're starting with a parent function, f of x, like x squared, um, and we're making these changes to the equation a, b, c, and d. All right, so we label them as capital letters, and we put them in alphabetical order, and that's to encourage you to do these from left to right, which is what we have to do. What we're going to talk about is what each of these does to the function, and then we're going to start putting them together, okay? But I will tell you that there's two different things that you need to be totally aware of before we start. That is, do the letters come inside the function or outside the function? What do I mean by that? When I read this, I read it as a times f of, and then plus d. So this b and the c, this is considered inside the function. And the a and the d are considered outside the function. Any change to the inside of the function, that is any change to the x's, whether it's by b or c, that changes your input. That changes your graph horizontally. It's a horizontal change, okay? If it's with the x, like the x-axis, it affects the graph horizontally. If it's outside the function, like a and d, that's affecting the outputs. That affects the y values. That affects the graph vertically. So that's the first dynamic you have to be aware of. Is it inside affecting the graph horizontally, or is it outside affecting the graph vertically? The second thing to be aware of is it multiplied like a and b? That's a times f of b times x. Those are multipliers. Or is it being added or subtracted like the c and d? That's also important because anything that's multiplied is going to be a stretch or a compression. It's a dilation. It changes the shape of the graph. So imagine having like some clay in your hands and you're pulling it apart vertically, or you're pushing it together vertically, or it could be you're stretching and compressing horizontally, almost like you're playing an accordion, right? Anything that is multiplied, like A and B, is going to be a compression, making it smaller, or a stretch, making it bigger. Whereas anything that's added or subtracted, like the C and D, that's a translation, we call it, or a shift. You're just picking something up and moving it either left and right or up and down. You're not changing the shape, you're just changing the location, okay? If you put those two things together, you'll have a much better understanding of how each of these works. Let me show you what I mean. A is being multiplied on the outside. Bless you. So that is a vertical dilation. That is either a vertical stretch or a vertical compression. That's what A does. It's a vertical stretch or vertical compression because it's being multiplied on the outside. B is being multiplied on the inside with the X. If you're multiplying on the inside, that's a horizontal stretch or horizontal compression. Okay? C is being added or subtracted on the inside. That then is going to affect the graph horizontally by shifting it or translating it, we say, left or right. It's just going to pick it up and move it left to right. And then D is being added on the outside, so that's going to be a vertical shift or a vertical translation. That just picks the graph up and moves it up or down D units. All right, let's try it out. I'm not going to go through all the words there because it could be kind of daunting. So what I'm going to do instead is this right here. What I'm going to do instead is I'm going to add a page. In fact, I'm going to add 2 pages if it'll let me. Yeah, there we go. I don't want to run out of room. We're going to look at each variable independently, okay? So let's look at this. Let's say we have g of x. Oops. Let's say we have g. Oops, I did it with highlighter again. G of x equals a times f of x, okay? We're going to take them one at a time. A is this is your vertical dilation factor, which means it is a stretch or compression. It can take on different values. So let's look. If the absolute value of A is greater than 1, I say absolute value because A can be negative, and we'll talk about that here in a second. But if the magnitude of A is bigger than 1, like 2, 3, 4, 5, whatever, it's going to be a vertical stretch by a factor of 1. And that's how we write it. V for vertical, S for stretch. That means we're making it bigger. And then BFO just means by a factor of, I'm sorry, not 1, sorry, by a factor of A. By a factor of A. Let me give you an example. Let's say that we start with a parent function. Let's use a different flavor here. Let's say we start with a parent function. We'll use this for all of them. Let's say we go back to the warm-up and we look at x squared. That's our parent function. Go ahead and make yourself a relatively nice graph of x squared so that we can reuse it. Make it kind of medium width. Something like that. There's your graph of x squared. Now what I want you to do is to copy it to your clipboard, right? Copy it to your clipboard because we're gonna use this every time. The example that I'm going to give you, we're going to contrast it. So here would be an example. An example would be if I have g of x equals, let's say, 4x squared. 4x squared. All right, here's what you're going to do. You're going to walk up to the problem. You're going to see 4x squared. You're going to notice that x squared is your parent function, x squared, and this 4 is being multiplied outside the square. Okay, it's outside the function. To be outside the x squared function means to be already have squared it. So if you think of your order of operations, you would pick your x value, you would square it next by your order of operations, and now you're outside the function. And the last thing you're going to do to these x squared values before you plot them is you're going to make them 4 times bigger. So what happens to the values? What's 4 times 0? 0. It would stay put. But if this y value were 1, what's 4 times 1? 4. It's up here. And if this y value were 2, what's 4 times 2? It's 8. It's way up here now. So what it's going to do, it's going to make the graph look like this. It's going to have the effect of making it steeper. Okay? Now, we can make this purple graph steeper visibly by either pushing it side by side to make the purple graph, but that's not what we're doing here. We're obtaining the purple graph by vertically stretching. So we're taking these values. If you want to draw arrows, this is what we're doing. We're vertically pulling these values. It's like you're grabbing this function. It's attached to strings, and you're pulling straight up on it. You're going to have the effect of making it narrower by a factor of 4. Okay? That's what we're doing. So what we would say then is this is a vertical stretch by a factor of 4. Vertical stretch by a factor of 4. 4 times taller. That's pretty straightforward. What if then the absolute value of A were between 0 and 1? Like 1/2, or 1/3, or 1/4, or 2/3, or 5/8, or anything less than 1 but greater than 0. That's going to be a vertical, guess what? Not stretch, but compression by a factor of BFO. And then here's the kicker. It's going to be by a factor of 1 over the absolute value of A. This is just the reciprocal. Okay, it's just the reciprocal. Let me show you what I mean. Let me give you an example. F of x equals 1/4 x squared. 1/4 x squared. You walk out to the problem, you see the x squared parent function, you see a 1/4 outside of it. You're going to take your x squared values, let's go ahead and paste it in here now. You're going to take these x squared values that are in green, but before you plot them, before you put your new dots, what are you going to do to all the values? You're going to take 1/4 of them, which makes them smaller by a factor of what? Do we say smaller by a factor of 1/4 or smaller by a factor of 4? They're smaller by a factor of 4. It's like a vector. We interpret the direction. We're making it smaller by a factor of the reciprocal. So this right here would be a vertical compression by a factor of 4. Not 1/4, 4, the reciprocal. So if you want to draw it in there, draw a parabola that's a little bit wider now. And instead of obtaining the purple graph from the green graph by horizontally stretching it, we're going to get the purple graph from the green graph by pushing all of these green values downward. So draw little arrows. We're pushing them downward. We're vertically compressing them by a factor of 4. It has the effect of making the graph wider. Okay? So like if this value were 1, now it's a 4th. If this value were 4, now it's 1. If this value were 8, now it's 2, so on and so forth. Okay? Now there's another thing. We keep using the absolute value of A because we can say this. If A is less than 0, this is a very special type of transformation. This means that A is negative. If A is negative, what it's going to do is it's going to make all of your positive Y values negative and all of your negative Y values positive. So this value here is going to be down here. This value here is going to be down here. This value here is down here. That's going to have the effect of making the graph open downward, like that. Oh, I didn't give you the example. This is going to be an x-axis, we say x-axis reflection. And an example would be f of x, or I should be calling this g of x. F of x is our parent function. Let me call this g of x. G of x equals negative x squared. Now you might have remembered that from Algebra 1. I believe when you started studying x squared, you met Mr. Parabola Man, did y'all? You met the parabola that opens up? And maybe you knew then that if x squared opens up, negative x squared opens down, okay? And why does it open down? Because it takes the original function and reflects it across the x-axis. All right, so you can actually have both of those combined. Like I could have a negative 1/4 x squared. If I had a negative 1/4 x squared, that would do two things. The negative would first reflect it across the x-axis, and then the 1/4 would make it wider by compressing it. So you could do them in sequence. You could do multiplication in any order, but it would be 2. So that takes care of your A. Your vertical stretch, vertical compression, and your reflection if it's negative. So far, so good? All right, let's move on to the letter B, and I'm going to move on to a new page. So now we'll look at g of x equaling f of b times x. B, oops, I don't want blue. B is this is your horizontal dilation factor. Okay, stretch or compression, stretch or compression. We have the same kind of criteria. If the magnitude of B, because it could be negative, is greater than 1. If it's bigger than 1, this is going to be a horizontal compression by a factor of B. Now this is kind of the opposite of what you might think. Let me give you an example here. If I have g of x equals parentheses 2x squared, like that. Okay, we walk up to the problem and I see that it's a squared function. But now instead of outside the square, I have parentheses, and inside the parentheses, I have something multiplied by the x. That tells you right there, because it's multiplied, that it's either going to be a stretch or compression, and because it's times the x, you know it's going to be horizontal. So it's either a horizontal stretch or a horizontal compression. Now here's where it's different for the B and the C. The insides are always opposite. You might look at 2 times x and think, hey, that's twice as wide, wouldn't you? 2 times x, twice as wide. But guess what? It's the opposite. It's not twice as wide, it's twice as small. It's twice as narrow. So this would actually be a horizontal compression, an HC, horizontal compression, by a factor of 2. We're scrunching it or compressing it by a factor of 2. And let's see what that graph would look like. If we put x squared here, horizontally compressing it is going to make a graph that's a little bit steeper again. But now, instead of getting the purple graph from the green graph by vertically stretching it, we're getting the purple graph from the green graph by pushing it in sideways like this. Like Alex Meixner playing the accordion, compressing those bellows. Everything comes in. The shape of it looks just like the graph of 4x squared, but now it's, bless you, 2x quantity squared. Horizontal compression by a factor of 2. Let's go ahead and put a little asterisk here and just say that this is the opposite of what it appears. Okay? And this is for all of your insides, your B and your C. Okay? It's opposite. So what would be the next possibility? If the absolute value of B is between 0 and 1. Again, like 1/2, 1/3, 1/4, so on and so forth. If it's opposite, this is going to be a horizontal stretch, an HS, by a factor of, and again, not B, but the reciprocal of B, 1 over B. 1 over B. Here's an example. G of x equals, parentheses, 1/2 of x quantity squared. So if you walked up to this problem, you'd see the squared function there, but on the inside with the x, you'd see a multiplier. That means right away you know it's going to be a horizontal stretch or compression, one of the two. Well, you might look at it and say, oh, 1/2 of the x, 1/2 of the width. That's going to be narrower, right? But guess what? Because it's on the inside, again, it's going to be the opposite of what it appears. So it's not half as wide, it is what? Twice as wide. Twice as wide. So what we would say is we would say that this is a horizontal stretch by a factor of not a half, but what? 2, the reciprocal of a half. All you got to do is flip it. We stretched it by a factor of 2 because it was a half. Whenever you say by a factor of, here's kind of the key. Whenever you say by the factor of, that number has to be bigger than 1. You never say by a factor of a half or by a factor of a fourth. If you do that, you need to flip that number because we're already interpreting if it's getting bigger or smaller. Okay? Let's see what the graph would look like. There's our old friend x squared, and now it's going to be a horizontal stretch, so it's going to have the same effect as the compression did earlier, but now we're getting from the green to the purple graph, not by pushing it downward and making it bow out, we're making it wider by grabbing those x values horizontally and literally pulling them out. We're stretching them horizontally. This would be the graph of G. All right, and then there's one last thing B could be. We could say if B is less than 0, that is if it's negative, that means all of your x values are going to trade places, right? So think about, let's put the x squared down here for this one. Go ahead and paste x squared in there. If B is negative, all of your x values change places. So you're going to have this x value coming across to that value. So a positive 3 is going to become a negative 3. A negative x equals 5 is going to be a positive x equals 5. So here is what it does. This is a y-axis reflection. A y-axis reflection. And here would be your example. If I have g of x equals, parentheses, negative x quantity squared. You would notice that on the inside, I'm multiplying by a negative 1. That means your x's trade places. Everything trades places like this across the y-axis. Now, what would the graph of g of x look like? If I took this graph of x squared and reflected it across the y-axis, what would you expect to see? Same thing, right? You wouldn't see a change, because x squared already has y-axis symmetry. So if you reflect it across the y-axis, you're not going to see a change. That could happen. Some functions you might not exhibit a noticeable change. Other functions, when you rotate them across the y-axis, they look very different. But in this case, we wouldn't see anything. And look, you could verify that algebraically. What would negative x times negative x be? What would happen to the negatives when you square it? To become positive x squared. So negative x quantity squared is exactly the same as x squared. And you can see graphically here, we don't see a change. So if you want to trace the new color for g of x on top of the old one here, in this case, you'll see no change. Now that takes care of the dilations and reflections. Those are the two that require the most thinking, okay? The shifts or the translations are the easier ones. That's the C and the D. I think I need to add another page. All right, let's come down here now and check out the next one. Let's say g of x now equals f of x minus c, like that. And now we're looking at the value of c. That is going to be your horizontal translation, also called a shift. I like to call them a shift because it implies just kind of scooting over. That's what translate means. We're not changing the shape anymore. We're not making it steeper or narrower by stretching and compressing. We're literally just picking the graph up and moving it left to right and setting it back down. That's it. Okay? So here's kind of the cases. If you see x minus c, that's going to move the graph right c units. If you see x minus c, you're going to move the graph right c units. Here's an example. Let's say we have g of x equals parentheses x minus 2 squared. When you walk up to the problem again, you notice it's the squared function, and now on the inside, affecting the x's, affecting the graph horizontally, we have something that's added or subtracted. That's going to be a translation or a shift. Now again, you might look at it and say, minus 2, negative 2, that's left 2, right? That would be your intuition, left 2. But guess what? Because it's on the inside, it's the opposite. So instead of being left 2, this one would actually be plus, yeah, it would actually move to the right 2. We want to do it in terms of a direction. It would be right 2 units, or we just say right 2. It's fine. So the opposite. Let's see what that would look like. If we put down our g of x again, here's what's cool. Since we're not changing the shape, you can actually just grab this and duplicate it. Well, hang on. I need to grab more of it because I did it in 2 pieces. You could just duplicate it, and now watch. You can actually count. If I pick my graph of x squared up and move it right 2 units, 1 unit, 2 units, and I set it right back down on the x-axis. And now I can trace over it in purple. That's the graph of g of x. And all we've done is we've moved it right 2. So the vertex is now at 2, 0 instead of 0, 0. That's it. Doesn't change the shape, just changes the location. All right, what if you see x plus c? If you see x plus c, it's actually going to be left c units. And here's the example. Let's say we have g of x equals x plus, let's do 3, let's use a different number, squared. You need to be able to look at the equation and tell what it's doing. It's squared, there's your function. We're inside doing something, so that's affecting the graph horizontally. It's not multiplied, so it's not a dilation. It's added or subtracted. Anything that's added or subtracted is just a translation. It's just a shift. Now again, your instinct might tell you then, okay, plus 3, that's to the right 3 units. But because it's on the inside, guess what? It's the opposite. And someday I'll tell you why it's the opposite, but I don't want to confuse that with you right now. So just realize if it's on the inside, a B or a C, it's the opposite. So instead of being right 3 units, it's what? This one's going to be left 3 units, or just left 3. So we can paste our x squared down. We can duplicate it. And now we could just pick it up and move it 1, 2, 3. We'll move it left 3 units. There's our new graph. We'll trace over it. Call it g of x. And now the vertex, which used to be at x equals 0, is now at x equals -3. Nothing to it, right? Inch by inch, it's a cinch. Piece by piece, it's a, what rhymes with piece? Piece by piece, it's a fleece. I don't know, that doesn't work. But inch by inch, it's a cinch, right? Piece of cake. All right, now that's it for C. We don't have to worry about what if C reflects it. C doesn't do that. C either moves it left or right. That's it, opposite of what it appears. So now we can look at the final letter, and that's D. If you look at g of x equals f of x plus d, notice now this d is being added outside the function. It's already closed. It's f of x, pause. Oh yeah, and before you graph it, add d to it. This is your vertical translation, or your vertical shift. Let's look at some examples here. So if I have g of x, if you see f of x plus d, that's going to be up d units. This one is exactly as it appears. You see plus d, it's not down d units, it's not opposite, it's outside, it's exactly as it appears. It's up d units. So here would be your example. Let's say we had g of x equals x squared plus 3. Notice now there's no parentheses, so the plus 3 is not inside. It's after the square, it's outside, it's affecting the graph vertically. This is going to move the graph up 3 units. And let's see what that would look like. Again, you could duplicate it. And now you could say, okay, up 3, that's 1, 2, 3. There it is. Trace over that in purple. Call it g of x. And now we know where the vertex is, right? The vertex is right there at 0, 3. We moved it up 3 units. And I guess there's one last direction we have to go, right? We went left, we went right, we went up, now we need to go down. So if you see g of x equals f of x minus d, that's down d units. Your example would be g of x equals x squared minus 2. That's going to be down 2. So let's see what that would look like here very quickly. There's the graph of g of x, our parent function. If I duplicate it, I move it down to 1, 2. Now we get that. Trace it in purple. Now we know the vertex is right here at -2. So the B and the C and the D are up, down, left, right. C is left, right. D is up, down. The A is your vertical stretch or compression, possible x-axis reflection. Your B is your horizontal stretch or compression, possibly a y-axis reflection. And that's it. The good news is we don't have to do these just one at a time. We could do these with a little bit of everything. In other words, we can have an equation that has an A value, a B value, a C value, and a D value all in one equation. And if we wanted to sketch what the resulting graph looks like, all we have to do is apply those transformations from left to right in the proper sequence. And if we just keep doing the result, what the next thing tells us to do, we'll get the answer. But we're not going to jump in right away with one of each of those altogether. We're going to do them in isolation. So let's, here's a summary if you want. Nice and colorful. Notice it does say on the inside for the B and the C, it says opposite. And it already has the negatives in there, so that just to remind you that they could be negative. Those are your reflections. All right. If you want to refer to that chart, you can. That's fine. I'm going to walk you through example 1. Describe the transformation from the parent function for each of the given g of x. So once again, we have some unknown parent function f of x. We'll just write this up here. Parent function f of x. Could be x squared, could be x cubed, could be the square root of x, could be sine of x, Could be anything. The graph is going to be affected the exact same way. So what is f of x plus 2? Here's what you do. You walk up to the problem, and you look to see where the change is made. This change is being made on the inside, right? It's inside the parentheses. It's on the inside, so it's going to affect the graph horizontally. It's being added or subtracted, so it's going to be a translation or a shift. So this is a horizontal shift. Is it left 2 or right 2? Left 2. And remember, the reason is not right 2 is because it's opposite. I'll just say opposite on the inside. The inside is always the opposite. I'll explain why some other time in the future. All right, come over here. F of x minus 2. Again, you walk up, you notice the changes on the inside, so it's horizontal. It's being subtracted, so it's a shift. Is it right 2 or left 2? This one is right 2. And you can put RT2, that's fine. And again, I'll just put opposite on the inside. All right, let's come over here to the next column. Now we got g of x is f of x close plus 2 on the outside. So when you walk up to this, you're like, oh, this is outside the function, so it's affecting the y values. It's affecting the function values. It's adding 2 to every single one of them, which moves it what? Up or down 2? Up 2. Okay, so this on the outside is exactly as it appears, not opposite. Up 2. This one over here then, f of x minus 2 should be what? Down 2. By the way, down 2 is the same phrase you would say if you had a dog at home, a big dog whose name was 2. Anyone have a dog named 2? And guests would come over and he gets excited and he starts jumping up on the guest. What would you say? Down 2. Down 2. And he say, good boy. Two times f of x. 2 times f of x. This one is outside the function, right? It's outside, so it's affecting the graph vertically. It's being multiplied, so it's a stretch or compression. So is this a vertical stretch or vertical compression? It's a stretch. It's exactly as it appears. It's twice as tall. So we're going to say VS for vertical stretch. BFO stands for by a factor of. And is it by a factor of 2 or 1/2? 2. Yeah. Whenever you say by a factor of, that number always better be bigger than 1. If it's not, flip it. Okay? Twice as tall. That's what that means. Whereas over here, you see a 1/2 being multiplied on the outside. That's still a vertical dilation, but because it's a half, it's half as tall as it used to be. And if something is half as tall as it used to be, that means we have vertically whatted it? Compressed it by a factor of what? 2, which is the reciprocal, I'll make this note here, of 1/2. Here's another one to practice. We'll call this a bonus example. What if I say g of x equals 2/3 of f of x? Is that a stretch or a compression? It's a compression because 2/3 is less than 1, right? So we'll say a vertical compression by a factor of, and of course it's by a factor of not 2/3, but 3/2 or 1.5. Yeah. If you compress something by a factor of 3/2, you're compressing it 1.5 times. So it's 1.5 times narrower, right? Oops, I put compression here. What should it be? That's right. Vertical compression, not narrower. It's shorter. It's shorter by a factor of 1.5. Okay, so if this number here, for either one of them, for a B or an A, if this number is ever between 0 and 1, you put BFO the reciprocal. Okay. All right, what about this guy? He's multiplied on the inside. Multiplied on the inside is a horizontal stretch or compression. Is it twice as wide or twice as narrow? It looks like a stretch, right? 2 times x, but it's on the inside, so it's actually the opposite. So again, it's not twice as wide. It's not stretched by a factor of 2. It's what? Horizontally compressed. So we put HC, horizontally compressed by a factor of 2. Yeah. Opposite on the inside. And my favorite one, what if I see f of 1/2 x? It's multiplied on the inside, so it's a horizontal something. Yeah, it's a stretch. You might think, oh, half as wide, but no, no, no. It's the opposite. So it's twice as wide. It's a horizontal stretch by a factor of what? 2. Yeah, the reciprocal of 1/2. So that one was exciting because you had to do the opposite and you had to flip it. That's the most fun one. You have to take the opposite of what it's showing and you flip it. All right, then to finish up these last ones here, negative in front, that's an x-axis reflection. We'll just go right to the bell here. An x-axis reflection on that one. And then if the negative's inside, it's a y-axis reflection. And that concludes our practice for example 1. Okay? Tomorrow we'll start doing more of these combined, and we'll finish this section. So make sure that you're looking at the homework for this section today sometime while it's still fresh in your head.